Hello class, this is the fourth video of our molecular clocks lecture, where we'll be taking a look at the transcription, translation, feedback loops, taking a look at the 24-hour clock to see which cycles correlate with different times of the subjective circadian day. So taking a look at our 24-hour clock here, note that the clock goes from 0 to 24 hours. Right, so this encompasses the whole day. And for the purposes of this exercise, hours 0 to 12 are subjective day, and from 12 to 24, which would be 0 of the next day, is our subjective night. And so we're going to arbitrarily start at hour 12. And so right here at the transition, right at dusk from day to night, we see on the molecular clock that we have high levels of timeless and period mRNA, which allows for time and period, the proteins to start to accumulate in the cytoplasm. Concentrations of time rise more slowly, and per is still being degraded by the double time protein DBT via phosphorylation. So you can see here in this graphic, right here at the transition to early night, subjective night, we see a peak increase of per and time mRNA. Per protein is increasing more rapidly than the time protein. So this time, per is still being broken down fairly regularly, has not been saved yet from timeless, and they have not formed high concentrations of the per time double time protein complex. Moving on, roughly around hour 15, and so we're still in early subjective night, but we're well past dusk. This is when we see the time protein concentrations rising substantially. It binds to per, the per double time complex, which protects per from degradation, right, which corresponds to this step right here. We have the complex that has formed between period, timeless, and double time, but still in the cytoplasm. About halfway through our subjective night, we see the time, period, double time complex accumulating in high quantities in the cytoplasm. And this is when we see phosphorylation by Soggy and Katie's kinase 2, which allows the complex to enter into the nucleus, as you can see here in this illustration. The complex is phosphorylated, allowing it to enter into the nucleus. Now we're in late subjective night. This is about the time in our molecular clock when the time per in DBT complex reaches its highest concentrations, which in the nucleus, which fully suppresses per in time transcription. Right, so we can see here it acts as a repressor on the cycle clock heterodimer, which facilitates the transcription of, among other things, per in time. And so that mRNA simply is not being made anymore here in late subjective night. As dawn approaches, per is very slowly degraded by DBT, right? So it does not have 100% protection from timeless in the complex, so it still degrades just a little bit. Right? And we start to see this sluggish degrade because there is no longer per or time being made. So this complex has reached its peak and there's no new proteins that are being made. So we start to see its concentration go down a little bit. Now we've reached dawn, right at the transition between the dark period and light period. And what we see here is that light triggers cryptochrome. It targets time and tags it for degradation. Cryptochrome is under the cycle clock E-box transcription control, and its concentrations build up overnight, and that primes this whole system to help quickly degrade timeless, and thus the whole time period double time complex during the morning. So we can see here, going back to our complex map of the molecular clock, cryptochrome, when exposed to light, tags time for degradation. During our early subjective morning, with timeless out of the picture, or it's no longer to protect per as much as it did before, per starts to degrade rapidly without time's protection via DBT. And as such, the cycle clock heterodimer is released from repression, and it is allowed to activate TIM and per once again. So the mRNA production starts up again as our TIM per DBT complex degrades. As you can see here with the complex out of the picture, per and TIM are mRNA increase rapidly. So throughout the rest of our subjective circadian day, the transcription of per and timeless rise, but the concentrations of the mRNA are not sufficient yet to stabilize period through the period timeless heterodimer during most of the day. So the concentrations just aren't high enough. As we discussed before, there's a bit of a lag between the production of mRNA and the subsequent production of the proteins themselves. This takes time. And if you remember, per is manufactured at a faster rate than timeless. So timeless lags and needs to catch up a little bit. So it takes most of the day before we actually see any sufficient concentrations of these proteins to protect period from degradation before they can start to form these complexes again. As we can see here. And then the next step is where we began, right at the transition between subjective day and subjective night, when there's sufficient timeless to protect per, and we have the double time period timeless complex that can form to be phosphorylated to enter the nucleus once again, and the cycle starts anew. Now let's take a look at our secondary transcription feedback loop. So specifically, we're taking a look at the production of the clock protein. So indicated here by the star on our 24-hour clock, this is the time that we see the clock concentrations, the clock protein concentrations, are near their peak. And so this is what's responsible for that positive feedback loop of the secondary loop, the positive arm. And this is responsible for the peak production of timeless and period mRNA concentrations, which, as we saw before, occur right around the same time. As the night progresses, we see concentrations of clock protein degrading. And during our late subjective night, clock concentrations are at their lowest. And this corresponds to the peak concentrations of the time per DBT complex. So during this time, that complex is at high concentrations, which has a repressive effect on the transcription of timeless and period mRNA. And clock is at its lowest, which has the same effect. It has a repressive effect on time in per. So the primary TTFL and the secondary TTFL, they go hand in hand. Right? So this is somewhat of a redundant process here. We have two different feedback loops, two different cycles that are resulting, complementing each other in the same ultimate repressive effects on transcription. And as we get to our early subjective day again, right after the lull in the clock protein, the clock begins to rise again as the day progresses, activating transcription of timeless and period more and more as the day goes on, which mirrors the production of the proteins period and timeless more and more as the day goes on.